The rotation of galaxies, often attributed to the mysterious presence of dark matter, might actually be a purely mechanical phenomenon, according to a groundbreaking model called cyclic quantum cosmology.
That's right, Isabella. This model proposes that the Big Bang isn't a magical beginning, but a kinematic event stemming from the primordial collision of multidimensional membranes. Space itself isn't a static vacuum, it's a dynamic fabric constantly generated by what we call quantum factories scattered throughout the universe.
So instead of a Big Bang, we have colliding membranes and space is somehow manufactured. That's a significant departure from standard cosmology. How does this apply to something as fundamental as galactic rotation, where current physics relies on dark matter to explain observed speeds?
Official physics currently explains the inexplicable speed of galactic peripheries by inventing dark matter, but in our mechanical model, we visualize the galactic center dominated by a supermassive black hole, not as a simple bottomless pit, but as a double-acting engine. Matter composing the galaxy continuously falls toward the black hole. Simultaneously, the galactic center constantly feeds new space, new geometric building blocks into the plane of the galaxy.
A double-acting engine, feeding space. That's quite an image. How does that translate into galactic rotation without needing dark matter?
Think of it as a cosmic treadmill. Matter acts like a runner moving on the belt, inexorably falling inward towards the black hole. But the treadmill itself pushes this newly created space outward, towards the galaxy's periphery. This outward flow of space drags the galactic periphery along, acting as a kinematic propeller. The density of matter accumulated toward the center acts as a fluid dynamic brake. The constant speed of rotation isn't a mystery, it's the result of this perfect mechanical balance between the space flowing outward and the matter falling inward.
That's a compelling mechanical analogy. It replaces an unknown substance, dark matter, with a dynamic interaction. But what happens when matter reaches the black hole's event horizon? Standard physics struggles with the information loss paradox. How does cyclic quantum cosmology address that?
In our mechanical model, information is never lost. It's an ironclad geometric law. When a fundamental constituent of matter, which we describe as an interaction between a string and a brain, reaches the heart of the black hole, a clear separation occurs. The string unties itself and returns to being pure geometric space, ready to be re-emitted into the flow. The brain, however, falls inside the black hole. During this fall, the brain fully and permanently retains all the structural information of the original piece of matter. The black hole, in this view, is the universe's safe, not its destroyer.
So the black hole safeguards information rather than obliterating it. That's a powerful shift in understanding. And what about the extreme conditions near a black hole, like spaghettification, where objects get stretched incredibly thin? How does your model explain that and the apparent slowing of time?
Astrophysicists observe the enormous geometric forces and tensions near the black hole's horizon. To understand this, we introduce a revolutionary concept. Time is a mechanical property of strings. Imagine the fabric of space-time as an elastic material. The unit of time is simply the mechanical tick-tock needed for a piece of matter to slide from one open string to the one immediately next to it, a simple shift of position.
Time as a mechanical tick-tock of strings. That's a very concrete definition. What does that mean for spaghettification?
Near a black hole, the geometric traction is so immense that the strings undergo extreme stretching, like a rubber band stretched to its maximum. This causes spaghettification. Matter is literally stretched and elongated because it's traveling on strings that are geometrically deformed and dilated beyond measure. This stretching also creates the paradox of time. Since the strings are stretched, the path matter must travel to pass from one string to another becomes much longer. Mechanically, the sliding slows down.
So for an observer far away, time for matter near the black hole would seem to almost halt. But for the falling matter itself, time flows normally, millimeter after millimeter, string after string. And this stretching also gives us a speed limit for the universe.
Precisely. The stretching of these strings establishes a fundamental physical law. There's a maximum limit beyond which the string's elasticity cannot stretch further or allow information to slide. This mechanical and geometric limit is the maximum impossible speed, which official physics calls the speed of light. This concept, based on the quantum mechanical principle of positioning, can explain the behavior of a photon with millimetric precision.
It sounds like every major cosmic mystery has a mechanical explanation within this framework. What about the expansion of the universe itself and the existence of vast cosmic voids?
Looking into deep space, the expansion of the universe isn't an equally distributed magical constant like the Hubble constant. Instead, it's a variable hydrodynamic phenomenon. The more space factories, which are intergalactic black holes, there are between two galaxies, the more space is injected, and the more rapidly those galaxies move away from each other. Where space was left orphan of its primordial counterpart after the collision of the branes, the great cosmic voids are born. These are bubbles devoid of internal geometric tension that expel matter toward the edges, creating the great filamentous walls of the observable universe. Everything is explained by the pressure and tension of a geometric fluid.
So, cosmic voids aren't just empty spaces, but areas lacking geometric tension, influencing the distribution of matter. This model of cyclic quantum cosmology offers a comprehensive mechanical explanation for so many cosmological phenomena, from galactic rotation to time dilation and cosmic expansion. It's a radical reimagining of our universe that moves beyond a two-dimensional understanding into a more complex three-dimensional model.
That's the ultimate goal. For simplicity, we focused on a two-dimensional visualization today, but this model will transform into a three-dimensional one, fully and precisely explaining the complex reality around us, including how the torsion, spin, and three-dimensional elasticity of strings create the texture of time and of light itself.
If these radical reimaginings of the cosmos sparked your curiosity, consider sharing this episode with someone who loves exploring the universe's deepest mysteries.